If you are lying in the dark right now, and somewhere nearby a light is glowing, a charging cable, a smoke detector, the faint pulse of a router's LED blinking in a corner of the room, take a moment to notice it. That small, unremarkable glow is the end of a very long story. A story that begins not with wires or switches or power stations, but with darkness. Pure, total, unmanaged darkness. Of the kind that no longer exists in most of the world. Because we have filled every corner of the night with the quiet, continuous presence of electrical light. If these quiet journeys through the history of human creation help you rest, consider leaving a like or subscribing. But for now, let the screens fade to black and let your breathing slow as we drift back into a world that had no switch to flick and no light waiting on the other side of it. The year is somewhere in the early 1500s, and the night has just arrived. Not the night that modern people know. The softened, ambient, electrically diluted darkness of a city where the sky is never fully black because the streets below it are never fully unlit. The night that has just arrived over this particular city in this particular century is something of a different order entirely. It is dark in the way that the inside of a closed box is dark, immediate, physical in its weight, the way cold is physical, something you feel against your skin rather than simply observe with your eyes. In the narrow streets below, the last of the evening's foot traffic is finding its way home by the light of handheld lanterns, small iron frames holding tallow candles behind thin panels of horn or oiled cloth, casting circles of yellowish light that move with their carriers and leave the spaces between them in absolute darkness. The lanterns sway slightly as their owners walk, producing a gentle, shifting pattern of light and shadow on the cobblestones below. Pools of amber warmth appearing and retreating, the darkness rushing back in behind each one as it passes. When the last lantern rounds the corner at the far end of the street, the darkness is total. Inside the buildings that line this street, life has reorganized itself around a single resource: fire. Not electricity, not gas, not anything that flows through a wire or a pipe. Only fire. The same technology that human beings had been using to push back the darkness for 200,000 years, unchanged in its fundamental nature. Since the first person crouched over a struck spark in the mouth of a cave and coaxed it into something that would last the night. In the kitchen of a prosperous household, tallow candles stand in iron holders on the heavy wooden table. Their flames, small and slightly unsteady in the drafts that move through the old walls of the building. The tallow is rendered animal fat, beef or mutton primarily, and it burns with a faint, organic smell that settles into the fabric of rooms and the fiber of clothing and the hair of the people who live in these spaces, a smell so constant and so universal that no one in this century would recognize it as a smell at all. It is simply the air. The candles produce light of a quality that is difficult to describe to someone who has never read by it. Warmer in color than any electric bulb, softer at the edges, alive in its slight continuous movement, but it is weak. A single candle illuminates a circle perhaps 2 feet in diameter, with enough reliability to read by, and the rest of the room beyond that circle exists in varying degrees of shadow. To light a large room adequately requires many candles. Candles cost money. Money is finite. Most rooms, in most households, in most of the world, are not adequately lit. The wealthy burn beeswax, which is cleaner and brighter, and produces less of the fatty smell that tallow leaves behind. In great houses and churches and the halls of institutions, chandeliers hold dozens of beeswax candles at once, their combined light producing something approaching genuine illumination. Enough to see faces clearly across a table, enough to read without straining, enough to work by into the evening hours. But even the wealthiest households in the world of the early 16th century go to bed earlier than they would choose to, because the cost of light, in candles, in oil, in the labor of tending flames through the night, imposes a discipline on the hours of darkness that electricity will one day dissolve entirely. The night is expensive, and so, largely, the night belongs to sleep. Outside the cities, in the villages and farms that house the majority of the world's population, the darkness is even more complete. A farmer in rural England, in a year, somewhere in the middle of the 1500s, rises before dawn and works until the light fails, because the light is the workday, and the workday ends when the light ends. And no amount of candles can extend a field's growing season or make a plowing run more visible in the dark. The rhythm of his life is set not by a clock. Clocks are rare, expensive, and imprecise enough to be of limited practical use to someone whose schedule is determined by sunrise and sunset, but by the movement of the sun across the sky and by the slow turning of the seasons that changes the length of each day in its gradual annual pattern. He sleeps when it is dark because there is nothing else practical to do when it is dark, and he wakes when the first light arrives, because the first light is the signal that the workday has begun again. This is not poverty exactly. It is simply the shape of a life organized around natural light in a world where no other kind exists. And yet, in this world of fire and darkness and tallow-smelling air, a few curious minds had begun to notice something small, something strange, something that had no name yet, because the thing it described had no framework in which to be understood. When a piece of amber, the golden fossilized resin that traders brought from the shores of the Baltic Sea, polished smooth and sold as jewelry and ornamentation, was rubbed briskly against a piece of wool cloth, it acquired a peculiar property. It attracted things, small things, feathers, dried leaves, tiny scraps of paper or cloth. These light objects, held near the rubbed amber, would move toward it without being touched, drawn across the small distance between them by a force that was not wind, not magnetism, not any of the known physical forces that natural philosophers of the era had identified and named. The amber pulled them, silently, invisibly, without any apparent mechanism. The ancient Greeks had observed this. Thales of Miletus, writing in the 6th century before the Common Era, had noted that rubbed amber seemed to attract light objects and had included this observation in his catalogue of nature's curiosities without explaining it. Because he had no explanation available, the observation had sat, patient and unexplained, in the margins of natural philosophy for 2,000 years, not because it was unimportant, because no one yet had the tools, the language, the experimental method, the conceptual framework to ask the right questions about it. In a study somewhere in London, in the last years of the 16th century, a physician named William Gilbert was beginning to ask them. Gilbert was a careful man, methodical in the way that the best scientific minds of any era are methodical. Not because methodology had been formally defined and taught to him, but because his particular temperament inclined him toward observation over assumption, toward the repeatable experiment over the inherited opinion. He had read everything that had been written about amber's strange attractive property. He had read Thales and the Roman authors who had mentioned it, and the medieval natural philosophers who had noted it without investigating it. And he had concluded, with the patient certainty of someone who has thought about a question long enough to know when the existing answers are insufficient, that no one had actually studied it properly. He decided to study it properly. In his study, by candlelight, in the particular stillness of a London evening settling into night outside his window, he began to collect materials. Amber, certainly, but also glass and sulfur and sealing wax and various gemstones and pieces of different metals and different types of cloth to rub against them. He rubbed each material against each cloth and held each combination near small test objects, a piece of dried straw, a fragment of leaf, a tiny scrap of thread, and observed carefully and repeatedly what happened. The candle on his desk burned steadily, its light falling across his hands and the materials arranged before him, and the pages of the notebook, in which he recorded each observation in small, precise handwriting. Outside, the London night was dark and quiet in the way that London nights were dark and quiet in the last years of the 16th century, completely and without apology and without any expectation that anything would ever change. Inside, the candle burned, and Gilbert wrote, and the long, slow story of electricity, which would take another 3 centuries to arrive at the switch on the wall, was beginning its first tentative steps toward the light. William Gilbert published his findings in the year 1600. The book was called De Magnete, on the magnet, and it was, by the standards of natural philosophy at the turn of the 17th century, an unusual kind of document. Most books of its era that dealt with the natural world were compilations of existing knowledge, careful arrangements of what Aristotle had said and what the Roman authors had added, and what the medieval scholars had preserved and annotated across the intervening centuries. De Magnete was different. It was built almost entirely on experiment, on things Gilbert had actually done in his study, with his own hands, with the amber and glass and sulfur, and various cloths he had collected and rubbed and tested and observed over years of quiet, methodical work by candlelight. He described his experiments precisely enough that another person could repeat them. He drew conclusions that the experiments supported and declined to draw conclusions that they did not. He was, in a manner that would not be formally named or taught for another generation, doing something that resembled what we would now call science. And in the middle of this careful, grounded book, he introduced a word. The word was electricus. It came from the Greek word for amber, electron, and Gilbert used it to describe the property that amber and certain other materials acquired when rubbed. The attractive force, the invisible pull that drew small light objects toward the rubbed surface without any visible mechanism connecting them. He called it the electric virtue in the Latin of his text, and he distinguished it carefully from magnetism, another invisible attractive force that was already well known. Now, by demonstrating through experiment that the two behaved differently in ways that made them clearly distinct phenomena. Magnets attracted iron specifically. The electric virtue attracted many different light materials indiscriminately. Magnets did not require rubbing to acquire their property. The electric virtue was created by friction and diminished over time without it. Magnets pointed north. Rubbed amber pointed at whatever small object happened to be nearest. Gilbert was precise about these distinctions. He was precise about most things. The word he introduced, electricus, electric, would survive every subsequent revolution. In the understanding of what he was describing, passing through Latin into every major European language, and from those languages into every other language on earth, until it became one of the most universally recognized words in human communication. He did not know this, of course. Writing in his study in London in the last years of the reign of Elizabeth I, the candlelight steady on his careful pages, he only knew that rubbed amber attracted things, that this behavior deserved a name, and that the name he had chosen seemed to fit. After Gilbert, the curiosity spread, not quickly and not in any organized way. Natural philosophy in the 17th century was not a coordinated enterprise with institutions and funding and shared programs of research. It was a scattered collection of individuals in different countries working largely in isolation, corresponding by letter when they corresponded at all, each one pursuing whatever questions their particular temperament and circumstance inclined them toward. The electric virtue was one of those questions. It was the kind of question that attracted a certain kind of mind. the kind that finds genuine pleasure in the careful observation of small, strange phenomena that is satisfied by the act of noticing rather than requiring the immediate construction of a grand explanation. Von Guericke, a German mayor and amateur natural philosopher, built in the 1660s what is generally considered the first electrical machine, a rotating sphere of sulfur that could be rubbed continuously by holding a dry hand against it as it turned, generating the electric virtue in quantities larger than any piece of amber rubbed by hand could produce. The sphere was mounted on a spindle and turned by a hand crank, and as it rotated against the friction of the operator's palm, it accumulated its charge in a way that could be demonstrated to observers. Small objects leaping toward the sphere, light materials streaming outward from it in thin threads, the occasional snap of a small spark visible in a darkened room. Von Guericke had built a machine for producing something he did not understand, using principles he could not explain, toward an application he could not imagine. This is, more often than not, how useful things begin. The decades passed, and the observations accumulated. In 1729, an English experimenter named Stephen Gray made a discovery that would prove, in retrospect, to be among the most significant in the early history of electrical science. Gray was not a young man when he made it. He was in his 60s, a retired cloth dyer who had taken up natural philosophy as the occupation of his later years, with the focused attention of someone who finally has the time to pursue the things that actually interest him. He had been experimenting with a glass tube, rubbing it with cloth to produce the electric virtue in the manner that Gilbert had described a century earlier, and he had noticed, somewhat by accident, that the attractive force the tube acquired could be made to travel, not just to objects held immediately near the tube, but to objects connected to the tube by a thread or a wire or a length of damp string. Gray spent months exploring this observation with the systematic patience of someone who understands that he has found something real but does not yet know its boundaries. He suspended a long line of damp hempen string from silk threads attached to the ceiling of his room. The silk chosen because, as he eventually determined, it did not allow the electric virtue to pass through it, while the hemp allowed it to pass freely. He connected one end of the string to a charged glass tube and held small test objects near the other end, sometimes 50 feet away, sometimes more. The objects moved. The electric virtue had traveled the length of the string from the tube and was attracting the test objects at the far end across a distance that would have seemed impossible to anyone reasoning from the assumption that the force was a property of the rubbed object alone. Gray called this property communication, the ability of the electric virtue to pass from one object to another through certain connecting materials. We call it electrical conduction, and the distinction he drew between materials that allowed the virtue to pass, conductors, and materials that did not, insulators, is a distinction that sits at the foundation of every electrical device that has been built in the 3 centuries since he made it. Gray shared his findings with the Royal Society of London, the institution that had been established in 1660 as a forum for the exchange of natural philosophical observations and experiments among the curious men of England. His letters were read at meetings attended by men who sat in quiet rooms lit by candles and listened to descriptions of experiments they could reproduce themselves with materials available from any market or workshop. This was the scientific community of 1729, not laboratories and universities and research grants, but a correspondence network of curious individuals, sharing observations by letter and meeting occasionally in rooms to discuss what they had found. Among those who read Gray's findings with particular interest was a Frenchman named Charles François de Cisternay Dufay. Dufay was a man of considerable energy and broad curiosity, employed as the superintendent of the French Royal Gardens, a position that gave him both resources and time to pursue the experimental interests that occupied the portions of his attention not required by horticulture. He repeated Gray's experiments. He extended them. He tested every material he could obtain to determine whether it was a conductor or an insulator, building a systematic catalog of electrical properties that nobody had previously compiled. And in the course of this work, he noticed something that Gray had not reported. There seemed to be 2 different kinds of electric virtue, not variations in strength or quantity, but genuine qualitative differences. The electric virtue produced by rubbing glass behaved differently in certain experiments from the electric virtue produced by rubbing amber or resin. Objects charged with one kind were attracted to objects charged with the other kind, but objects charged with the same kind repelled each other, pushed apart with the same invisible force that usually pulled things together. Dufay named these 2 types vitreous electricity and resinous electricity, after the glass and resin that produced them respectively. He published his findings in 1733 in the careful, measured language of a man who was describing what he had observed, rather than claiming to explain it. He had observed correctly. The explanation, the underlying nature of the 2 types he had identified, would come from someone else in a different country 2 decades later. The rooms where all of this work happened were quiet rooms. Not quiet in the way that we imagine silence now, with its connotations of emptiness and absence. Quiet in the way that rooms are quiet when the work being done in them requires concentration, a background hum of ordinary life present, but unattended to the creak of a wooden floor, the distant sound of a street, the small sounds of the experimenter's own movements as he arranged his materials and made his observations. The glass tubes lay on the workbenches, smooth and cool to the touch. The silk threads that suspended Gray's conducting strings from the ceiling caught the light when the candle moved, fine and nearly invisible. The small test objects, scraps of thread, pieces of dried leaf, fragments of beaten gold leaf, so light. They moved in the breath of a person standing near them, waited on the wooden surfaces for the moment when the tube would be charged and the experiment would begin again. Each experimenter worked largely alone. Each added something small to a structure that none of them could see whole, because the structure did not yet exist as a whole. It was being built, piece by piece, observation by observation, in quiet rooms across 2 countries, over the course of a century and a half. Outside, the world went about its business without electricity, lit by candles and fires, moving at the speed of horses, entirely unaware that in these quiet rooms, something was being assembled that would eventually change every aspect of the life being lived outside. The glass tubes were rubbed, the test objects moved, the notes were written, and the slow, patient work of understanding continued, one careful observation at a time, into the long, dark evenings of the early 18th century. Benjamin Franklin was not, by the standards of the natural philosophers who had preceded him, a formally educated man. He had left school at 10 years old. He had taught himself to read Latin and French by working through books in the evenings after long days of labor in his brother's printing shop in Boston, the candlelight low, and the hour late, and the books borrowed from whoever would lend them. He had educated himself in the particular way that self-taught people educate themselves, deeply in the things that interested him, broadly in everything else, with the particular confidence of someone who has never been told which questions are too large for him to ask. By the time he encountered the subject of electricity in the early 1740s, he was already a successful printer, a civic organizer, a founder of libraries and fire departments, and philosophical societies, a man whose practical intelligence had been demonstrated across a wide range of endeavors, and whose curiosity showed no signs of narrowing with age. He was also, by his own account, immediately and completely captivated. His introduction to electrical experiment came in 1743, when he attended a demonstration in Boston by a Scottish physician named Archibald Spencer, who was touring the American colonies with a traveling exhibition of electrical phenomena. The glass tubes, the electrical machines, the sparks and attractions and repulsions that had been delighting and puzzling European audiences for decades. Franklin watched the demonstration with the focused attention of someone encountering, for the first time, a phenomenon that his existing mental framework cannot accommodate. He bought Spencer's equipment when the tour ended. He set it up in his house in Philadelphia and began experimenting, writing about what he found in letters to a friend in London named Peter Collinson, who arranged for the letters to be read before the Royal Society, and eventually published in a pamphlet that circulated among the natural philosophers of Europe. The letters were written in Franklin's characteristic style, plain, direct, occasionally funny, entirely without the ornamental Latin that decorated most scientific writing of the era. He described his experiments the way he described everything, as if he were telling a story to an intelligent friend who deserved a clear account rather than an impressive one. What Franklin contributed to the understanding of electricity was not simply more observations. He contributed a framework, a way of thinking about what electricity was and how it behaved that organized the scattered observations of the previous century into something coherent. He proposed that electricity was a single fluid, not two different types, as Dufay had suggested, but one substance that could be present in excess or in deficit in any given object. An object with too much of this fluid was positively charged. An object with too little was negatively charged. When the two were brought together, the fluid flowed from the excess to the deficit until balance was restored. And this flow was what produced the spark, the attractive force, the repulsion. He was wrong about the fluid. Electricity is not a fluid in any literal sense, but the framework he built around the idea. Positive charge, negative charge, the flow from one to the other, described the behavior of electrical phenomena with enough accuracy that it remained useful for over a century, and the language he introduced persists to the present day. Every time someone speaks of positive and negative terminals, of charge flowing from one place to another, they are using a vocabulary that Franklin assembled in his Philadelphia house in the 1740s, writing letters by candlelight to a friend in London. The kite experiment happened in the summer of 1752, and it happened the way that Franklin's best work tended to happen, quietly, with minimal apparatus, in the service of a question that had been forming for years. The question was whether lightning was electrical in nature. This was not, in 1752, an established fact. It was a hypothesis, one that Franklin had been developing through his experiments with electrical machines and Leyden jars and the behavior of pointed metal conductors. The behavior of lightning, as he understood it from observation, matched the behavior of the electrical sparks his apparatus produced, scaled up to a magnitude that natural forces seemed to operate on, and human apparatus did not. If lightning was electrical, then it could, in principle, be attracted to a pointed conductor raised into the air, the same way that small sparks were attracted to the pointed rods. In his laboratory experiments, he went out into a field on a stormy afternoon with his son William, a simple kite made of a silk handkerchief stretched across a crossed wooden frame, a length of hemp string, a key tied to the bottom of the string, and a length of silk ribbon between the key and his hand, the silk serving as an insulator to prevent the charge from flowing into his body. The kite went up. The storm moved overhead. For a long while, nothing happened. Then Franklin noticed the loose fibers of the hemp string beginning to stand away from the line, each one erecting itself independently, repelled by the charge accumulating in the string from the electrified air of the storm. He brought his knuckle near the key. A spark jumped. The implications were immediate and practical in a way that purely theoretical discoveries often are not. If lightning was electricity, and if electricity was attracted to pointed metal conductors, then a pointed metal rod mounted on the roof of a building and connected by a wire to the ground would attract lightning strikes away from the building itself, conducting the charge safely into the earth before it could ignite the structure. Franklin installed the first lightning rod on his own house in Philadelphia and published instructions for others to do the same. The lightning rod spread across the American colonies and then across Europe with a speed that few technologies of the era could match because its benefit was immediate, visible, and required no understanding of the underlying science to appreciate. Buildings that had lightning rods did not burn when struck. Buildings that did not have them sometimes did. The argument was persuasive. The years that followed Franklin's kite experiment were years in which electricity moved slowly from the status of a philosophical curiosity to the status of a phenomenon's dark, whose practical implications were beginning to be imaginable, not yet realized. The gap between imagining that electricity might do useful things and actually making it do useful things was still enormous and would remain enormous for another century. But the imagination was there. In laboratories across Europe, experimenters worked with the Leyden jar, a device for storing electrical charge, invented in the Netherlands in 1745, consisting of a glass jar coated inside and outside with metal foil, capable of accumulating a charge from an electrical machine and discharging it in a single, powerful spark. The Leyden jar could discharge through a chain of people holding hands, sending a simultaneous jolt through dozens of bodies at once, a demonstration that became a popular entertainment at aristocratic gatherings. The guests holding hands in a long line while the person at one end touched the charged jar. And everyone felt the shock simultaneously, producing startled laughter and the particular exhilaration of having experienced that defied easy explanation. It was spectacle, primarily amusement for the educated and the curious, but it was also, in its clumsy way, a demonstration of something important, that electricity could travel through a human body, which meant that it could travel through any conducting material, which meant that its movement could, in principle, be directed and controlled. The direction and control were still a long way off. But in the quiet spaces between the demonstrations, in the careful notes of the experimenters, who watched and recorded, rather than simply marveled, the questions that would eventually lead there were forming. Franklin returned to his printing business and his civic life, his electrical experiments gradually giving way to the other demands of a life that had always had too many interesting things in it. He would go on to become a diplomat, a statesman, a founding father of a nation, a figure whose face would eventually appear on currency. But the kite and the key and the spark that jumped to his knuckle on a stormy afternoon in a Philadelphia field, these remained in the long accounting of his contributions to human knowledge, among the most significant things he ever did. Not because they were dramatic. The experiment itself was simple, almost absurdly so. A homemade kite, a piece of string, a key, but because they answered a question that had frightened human beings since the first storm rolled across the first sky. Lightning was not divine anger, or supernatural force, or the unknowable expression of powers beyond human comprehension. It was electricity, and electricity, as Franklin had spent a decade demonstrating, was something that could be studied and understood, and, in time, used. The storm passed over Philadelphia. The kite came down. The key cooled. And somewhere, in the accumulating knowledge of what electricity was and how it behaved, the long road toward the switch on the wall had taken one more quiet step forward. For most of the 18th century, electricity had been a thing of moments, a spark, a shock, the brief, violent discharge of a Leyden jar releasing its accumulated charge. In a single instant, the energy gone as quickly as it arrived, leaving nothing behind but the faint smell of something sharp in the air, and the tingling in the hands of whoever had been holding the device. This was the fundamental limitation of everything that had been done with electricity since Gilbert named it, and Gray conducted it, and Franklin pulled it from a storm cloud with a kite and a key. It could not be sustained. You could accumulate a charge, and you could release it, and the release was dramatic and sometimes useful and always interesting. But you could not make it flow continuously in a steady stream for any useful length of time. Without continuous flow, electricity remained a curiosity, a demonstration, a thing that happened and then stopped. What was needed, though no one yet knew precisely how to say this, was something that could produce electricity not as a single accumulated burst, but as a steady, controllable current. Something that would keep the electricity moving like water through a pipe for as long as the device was operating. That something arrived almost accidentally from the twitching legs of a dead frog. Luigi Galvani was a physician and anatomist at the University of Bologna, a careful and methodical man whose primary interest was the study of the human body rather than the study of electricity. In 1780, he was conducting experiments on the nervous systems of frogs, dissecting them, studying the structure of their muscles and nerves, attempting to understand the mechanisms by which the body produces and transmits the signals that cause muscles to contract. Electrical machines were common laboratory equipment by this point, used to produce sparks for various experimental purposes, and Galvani had one in his laboratory. At some point during his work, the exact circumstances are not entirely clear from the historical record. He noticed that the dissected legs of a frog lying on a metal surface near the electrical machine twitched when a spark was produced nearby. He did not yet understand what he was seeing, but he recognized that he was seeing something. He began to investigate with the careful patience of someone who has found a phenomenon he cannot immediately explain and has decided that the inability to explain it is a reason to look more carefully rather than a reason to move on. He varied the conditions. He changed the distance between the frog legs and the machine. He tried different metals on the surface beneath the legs. He applied the electrical charge directly to the nerves rather than producing it nearby the legs. Twitched consistently. Something in the electrical disturbance was causing the muscles to contract in a manner that resembled, though Galvani did not put it quite this way, the contractions that occurred in living animals during normal movement. He concluded, after years of further experiment, that the electricity producing these contractions was not coming from the machine. It was coming from the animal itself. Living tissue, he believed, contained its own electrical fluid, a biological electricity that was distinct from the electricity produced by friction or Leyden jars. An animal electricity that was the fundamental force behind all muscular movement and nervous sensation. He published these conclusions in 1791 in a careful Latin treatise that circulated through the natural philosophical community of Europe and was read, among others, by a physicist in Pavia named Alessandro Volta. Volta read Galvani's work with the focused attention of someone who respects a colleague's observations while doubting his conclusions. He repeated Galvani's experiments. He obtained his own frogs, his own metals, his own electrical apparatus, and he worked through the experimental protocol that Galvani had described, observing carefully what happened and thinking carefully about what it meant. His conclusion was different from Galvani's. The electricity causing the frog legs to twitch was not coming from the animal. It was coming from the contact between two different metals. The different metals in the circuit that Galvani had inadvertently created when he placed the frog tissue on one metal surface and touched it with instruments made of another. Two different metals separated by a moist conducting substance produced an electrical potential between them. The frog tissue was simply the conductor that allowed the resulting current to flow, and the visible twitching of the muscles was the consequence of that current passing through them. The animal itself was not the source of the electricity. The animal was the detector. Having arrived at this conclusion, Volta did what the best experimental minds tend to do with a new understanding. He pushed it as far as it would go. If two different metals separated by a moist conductor produced an electrical potential, what happened if you stacked many such pairs on top of each other. He built it to find out. The device he constructed in 1800 consisted of alternating discs of zinc and copper, each pair separated by a disc of cloth or cardboard soaked in brine, salt water, which conducted electricity more readily than plain water. The discs were stacked in a column, zinc and copper, alternating with the wet separators between them. The whole assembly held together by its own weight into a vertical pile, perhaps a foot tall. He connected a wire to the zinc disc at the bottom and another wire to the copper disc at the top, and he found that a continuous electrical current flowed through any conducting material, connecting the two wires. Not a spark, not a momentary discharge. A continuous, steady flow of electrical current maintained for as long as the chemical reactions within the pile continued, which was, in the first versions, a matter of hours. He called it the voltaic pile. The world would eventually call it the battery. The voltaic pile produced its current in a room in Pavia that was cold in the way that Italian stone buildings are cold in winter. Thoroughly, deeply cold, the chill coming from the walls and the floor as much as from the air. The pile itself sat on a wooden workbench, an unassuming column of metal discs and wet cloth that gave no visual indication of what was happening within it. No glow, no spark, no movement. Only the quiet, invisible flow of current through the wires connecting its terminals, detectable only by its effects. The deflection of a compass needle held near the wire, the small shock felt when both wires were touched simultaneously, the slow decomposition of water into bubbles of gas when the wires were submerged in a dish of liquid. Volta announced his discovery in a letter to the Royal Society of London in March of 1800, describing the construction of the pile and the continuous current it produced with the careful precision of someone who knows. He is describing something that has not existed before and wants to make certain that others can reproduce it. The letter was read at a meeting of the Society, and its contents spread through the scientific community of Europe within weeks. The response was immediate. Within months, laboratories across Europe and England had built their own voltaic piles and were using the continuous current they produced to perform experiments that had been impossible with the fleeting discharges of Leyden jars. Water was decomposed into hydrogen and oxygen by passing current through it. The experiment that established the field of electrochemistry and opened an entirely new domain of chemical investigation. Metals were deposited from solutions onto conducting surfaces by the action of the current, the beginning of electroplating, and in a laboratory in London, a young man who had grown up in poverty and educated himself in the reading rooms of the Royal Institution was beginning to think about what else a continuous electrical current might be made to do. His name was Michael Faraday, but that is the story of the next chapter. For now, in the first years of the 19th century, the voltaic pile sat on its workbench in laboratory across Europe, its column of disks quiet and still, its current flowing invisibly through the wires connected to its terminals. The candles burned around it, as they had always burned, casting their warm and unsteady light across the wooden surfaces and the careful notebooks and the hands of the people working in these rooms. But something had changed. For the first time in the history of human engagement with electricity, the current did not stop when the spark ended. It flowed on, steadily, patiently, for as long as the pile had chemical energy remaining within it. The darkness outside the laboratory windows was the same darkness it had always been, complete and indifferent and unaware of what was being assembled, one careful experiment at a time, in the lit rooms within. But the rooms themselves were different now. Something was flowing in them that had never flowed before. And the long, patient work of learning what to do with it had just begun. Michael Faraday was born in 1791 in a small house in Newington Butts, a village south of London that has long since been absorbed into the city's sprawl and forgotten as a place with its own name and character. His father was a blacksmith, frequently ill, unable to work consistently, and the family lived in the particular way that families live when income is unreliable, and the city around them offers no safety net beyond the charity of neighbors and the church. There was enough to eat, usually. There was not much else. Faraday left school at 13 and was apprenticed to a bookbinder named George Rebow, whose shop on Blandford Street in Marylebone became, for the next 7 years, both his workplace and his library. The arrangement was unusual in its generosity. Rebow allowed his apprentice to read any book that came through the shop for binding, and books came through in considerable variety, on subjects ranging from theology to natural philosophy to household management to the emerging sciences of chemistry and electricity. Faraday read everything, but he read the science with a particular intensity, taking notes in small notebooks he kept in his coat pocket, copying passages he wanted to remember, drawing diagrams of apparatus described in texts he could not afford to purchase. He was educating himself in the only way available to him. Slowly, incrementally, in the margins of paid work, by the light of whatever lamp the shop provided. In 1812, a customer of Rebow's gave Faraday tickets to attend 4 lectures at the Royal Institution by the chemist Humphrey Davy, then the most celebrated scientist in England, famous for his discoveries in electrochemistry and for his gift for making complex science comprehensible to general audiences. Faraday attended all 4 lectures. He took detailed notes in his careful, small handwriting, filling nearly 90 pages with transcriptions of Davy's arguments and descriptions of his demonstrations, then bound the notes himself and sent them to Davy with a letter asking whether there was any position available at the Royal Institution. Any position at all. including the most junior laboratory work. Davy read the notes. He was impressed by their precision and completeness. When a position as a laboratory assistant became available in 1813, he offered it to Faraday. Faraday accepted immediately, quieter, leaving the book-binding apprenticeship for a salary smaller than what Ribau had paid him, because the work itself was what he wanted, and the salary was a secondary consideration. He was 21 years old, and he had just entered the building where he would spend the next 45 years of his life. The Royal Institution occupied a townhouse on Albemarle Street in Mayfair, and its basement laboratories were the kind of spaces that accumulate character slowly. Low ceilings, stone floors worn smooth by decades of use, shelves holding the organized accumulation of apparatus and chemicals, and reference materials that serious experimental work requires. Faraday's early years there were spent largely in assistance, setting up Davy's experiments, maintaining the equipment, preparing chemical samples, learning the practical craft of experimental science from proximity to someone who practiced it at the highest level. But he was also conducting his own experiments in the hours before and after the official working day, at the same benches where Davy's more celebrated work was done. The benches smelled of chemicals, the sharp bite of acids, the heavier odor of sulfur compounds, occasionally the sweeter smell of organic solvents being distilled in glass apparatus over small flames. The candles, and later, the gas lamps that lit the basement, cast a warm and slightly unsteady light across surfaces crowded with the tools of the work: glass vessels, metal conductors, coils of wire, the batteries that provided the electrical current for experiment. It was in these rooms that Faraday would do the work for which he is remembered. In 1820, a Danish physicist named Hans Christian Ørsted made an observation that redirected the attention of every electrical experimenter in Europe. Ørsted was conducting a lecture demonstration, showing his students the properties of electrical current from a voltaic pile, when he noticed that a compass needle placed near the wire carrying the current deflected from its usual orientation. The needle pointed north when no current was flowing. When current flowed through the nearby wire, the needle swung away from north and pointed in a different direction, determined by the position of the wire relative to the needle. He had not been looking for this. He was demonstrating something else entirely. But he recognized immediately that what he was seeing was significant. That electricity and magnetism, which had been considered entirely separate phenomena, since Gilbert had distinguished them 2 centuries earlier, were in fact connected in a way that nobody had previously suspected. Electricity produced magnetism. A current-carrying wire behaved like a magnet. The news spread through European scientific circles within months, and experiments began immediately in laboratories from Paris to London to Copenhagen, each one probing the relationship between electrical current and magnetic force. from a different angle, adding new observations to a picture that was growing rapidly but was not yet coherent. Faraday read Orsted's report with the concentrated attention he gave to everything that arrived in the Royal Institution's reading room. He repeated the experiment. He verified the observation. And then he did what Faraday characteristically did. He thought about it for a long time before acting, turning the observation in his mind. The way a craftsman turns a piece of material, looking for the implications that were not immediately obvious. If a current-carrying wire produced a magnetic force around it, he reasoned, then perhaps a magnetic force could produce a current in a wire. The logic seemed to him sound. If the relationship between electricity and magnetism was real and fundamental, it should work in both directions. The ability to create magnetism from electricity should imply an ability to create electricity from magnetism. This inference, simple to state, enormously difficult to demonstrate, became the organizing question of the next decade of his working life. He built apparatus. He wound coils of wire around iron cores. He moved magnets near conducting wires and watched for any indication that current was being produced. He varied the configuration, the speed of movement, the strength of the magnet, the number of turns in the coil, with the methodical patience of someone who is not certain the effect he is looking for exists, but is not willing to conclude that it does not until he has exhausted every reasonable variation. For 10 years, he found nothing consistent. On the 29th of August, 1831, in the basement laboratory of the Royal Institution, Faraday wound two separate coils of wire around opposite sides of an iron ring. He connected one coil to a battery and the other to a sensitive current-detecting instrument called a galvanometer, which indicated the presence of electrical current by the deflection of a small needle. When he connected the battery to the first coil, the galvanometer needle connected to the second coil twitched, not continuously, only for an instant. At the moment the current in the first coil began to flow, then the needle returned to zero, even though the current in the first coil was still flowing. When he disconnected the battery, the needle twitched again in the opposite direction and returned to zero. He sat very still and looked at the galvanometer for a long moment. The needle had moved. In the second coil, connected to no battery, current had appeared, created not by a chemical reaction, but by the changing magnetic field produced by the first coil. When the current in it started and stopped, it was not the continuous current he had been looking for, but it was current where no current had been before, produced by magnetism rather than chemistry. He continued working, quickly now, following the observation wherever it led. Within weeks, he had demonstrated that moving a permanent magnet in and out of a coil of wire produced a continuous current in the wire, as long as the magnet kept moving. Motion producing current. Magnetism producing electricity. The electrical generator had been invented, in principle, in a basement in Mayfair by a blacksmith's son who had educated himself by reading the books he was paid to bind. Faraday did not patent his discoveries. He did not seek wealth from them. He continued working in the same basement rooms, on the same stone floors, at the same wooden benches, for another 20 years after the discoveries that would eventually transform the world. He grew older in those rooms. His hair went gray. His memory, in the last years, became unreliable in ways that distressed him. But the work continued, patient and careful, and entirely without urgency, as if the man doing it understood that the things he was finding were real, regardless of the speed at which he found them, and that being right was more important than being first. Outside the basement windows, London went about its ordinary life. The sounds of the street drifting down through the stone, the smell of coal smoke that hung over the city in all seasons, the distant sound of horses on the paving. Inside, Faraday moved between his benches in the quiet of the laboratory, adjusting his coils and his magnets and his galvanometers, recording his observations in the notebooks that would eventually fill thousands of pages. He had found the principle on which every electrical generator ever built would operate. Every power station, every turbine, every dam with water turning its wheels in the dark below. He had found all of this in a basement, alone by the light of a gas lamp. On a Tuesday morning in August, he wrote it down. He continued working. The lamp burned steadily. The needle of the galvanometer rested at 0, waiting for the next experiment to begin. By the 1880s, the pieces were in place. Faraday had demonstrated that magnetism could produce electricity, and that electricity could produce magnetism. The decades following his basement discoveries had been spent by engineers and mathematicians translating his experimental findings into practical machinery. Generators that converted mechanical motion into electrical current, motors that converted electrical current back into mechanical motion, transformers that changed the voltage of alternating current from one level to another. The science was understood well enough. The engineering was mature enough. What remained was the question of how to get the electricity from where it was generated to where it was needed. This question, simple to state, enormously complex to answer, would produce the most consequential commercial and technical battle of the 19th century, fought between two men whose temperaments were so different that their conflict was perhaps inevitable from the moment they occupied the same room. Thomas Edison had not discovered anything fundamental about electricity. What he had done, which was in its own way equally significant, was build the infrastructure to make electricity useful. His laboratory at Menlo Park, New Jersey, was unlike anything that had existed before it. Not a single experimenter working alone at a basement bench, but a staffed facility with multiple buildings, a machine shop, a library, and a team of engineers and craftsmen working simultaneously on different aspects of whatever problem Edison had decided to solve. The incandescent light bulb, perfected in 1879 after thousands of experiments with different filament materials, was the product of this organization as much as of Edison's own genius, a result of systematic, parallel testing carried out by multiple people under Edison's direction. But the light bulb alone was not sufficient. A light bulb required electricity, and electricity in 1879 was not something available in any house or business in the world. It had to be generated and transmitted and distributed to the point of use through a network of conductors. Edison designed this network. His system used direct current, electrical current that flows in one direction only, at a fixed voltage. The Pearl Street Station in Lower Manhattan, which opened in September of 1882, was the first commercial electrical power station in the world, delivering direct current to 59 customers within a roughly 1 mile radius of the station. The customers' buildings had been wired in advance. The meters had been installed. On the afternoon of September 4th, 1882, Edison himself threw the switch at Pearl Street, and the lights in the offices of the New York Times and the banking house of J.P. Morgan came on. It was, by any measure, an extraordinary achievement. It was also, as a young Serbian engineer who had recently arrived in America was beginning to understand a system with a fundamental and possibly fatal flaw. Nikola Tesla had come to work for Edison in 1882, arriving in New York with the particular intensity of a man who has been thinking about electrical problems for years and has arrived at conclusions that the existing state of the art has not yet reached. His conclusion, developed through mathematical analysis and physical intuition in equal measure, was that direct current was the wrong system for large-scale electrical distribution. The problem was voltage and distance. Direct current could not easily be transformed from one voltage to another. This meant it had to be transmitted at the voltage at which it would be used, low enough to be safe in homes and offices, and low voltage, direct current lost an enormous proportion of its energy to resistance in the wires over any significant distance. Edison's Pearl Street Station could serve customers within a mile of the generator. Beyond a mile, the losses in the wire became too great to overcome economically. A city could be served by many small generating stations, placed close enough together that no customer was more than a mile from one. But a continent could not be served this way. The countryside between cities, the farms and villages and towns that lay beyond the radius of any practical direct current network would remain in darkness. Tesla believed that alternating current was the solution. Alternating current reverses direction many times per second, 60 times per second, in the system that would eventually become standard. This property, which seemed at first like a complication, was actually its crucial advantage. because alternating current could be transformed from low voltage to high voltage and back again using simple electromagnetic devices called transformers. High voltage alternating current could travel hundreds of miles through wires with acceptable losses. At the destination, a transformer would step the voltage back down to a safe level for use in buildings. The same generating station could serve not a 1-mile radius, but an entire region. Edison was not interested in Tesla's ideas. His investment, financial, intellectual, reputational, was in direct current. The Pearl Street Station existed. The infrastructure was being built. The patents were held. Changing systems now would mean abandoning everything already constructed and starting again. Tesla left Edison's organization and eventually found support from George Westinghouse, a Pittsburgh industrialist who had built a successful business in railway air brakes and recognized in Tesla's alternating current system the potential for something much larger. What followed became known in the history of electrical engineering as the War of Currents. Edison fought the adoption of alternating current with the particular ferocity of a man protecting something he has built from nothing. He organized public demonstrations in which animals were electrocuted using alternating current, arguing that its higher voltages made it inherently dangerous for public use. He lobbied regulators. He campaigned in newspapers. The campaign was effective in generating attention. It was not effective in changing the underlying physics. In 1893, Westinghouse and Tesla won the contract to illuminate the world's Columbian Exposition in Chicago using alternating current, a demonstration visible to 27 million visitors that the system worked safely and reliably at scale. In 1895, the Niagara Falls Power Station began transmitting alternating current generated by the falls to the city of Buffalo, 20 miles away. The distance was impossible for direct current. For alternating current, it was routine. The war was over. The grid that would eventually carry electricity to every home and factory and street lamp on Earth would be built on alternating current on the principles that Tesla had understood in the mathematical workings of his own mind before he had ever built a single piece of hardware to test them. Edison's direct current stations continued operating for years. The last one in New York was not shut down until 2007. But the future belonged to the system that could travel farther than a mile. It always had. The Niagara Falls Power Station did not look, from the outside, like the beginning of a new world. It was a large stone building on the American side of the falls, solid and rectangular, its architecture borrowing the heavy civic dignity of the public buildings of the era. Arched windows, dressed stone, the kind of construction that announced permanence and institutional seriousness without drawing attention to itself. Inside, the turbines ran continuously, driven by water falling from a height through steel. stocks buried in the rock beneath the building, each one turning a shaft connected to an alternating current generator designed to Tesla's specifications and built by Westinghouse's engineers. The generators were large machines, iron and copper wound together in configurations that Faraday had described in principle in his basement laboratory 60 years earlier, now realized at a scale and precision that Faraday could not have imagined from his equipment. They turned without stopping, day and night, their rotation smooth and constant, driven by water that had been falling over the same escarpment for 10,000 years. Before anyone thought to put a turbine in its path, the current they produced traveled outward through thick copper cables, stepped up to high voltage by transformers before leaving the building, the voltage high enough to carry the power 20 miles to Buffalo with acceptable losses in the wire. In Buffalo, other transformers stepped the voltage back down. The current entered the city's distribution network and flowed through smaller cables to the buildings connected to it, where it powered the motors and the lights that were, by 1896, beginning to multiply throughout the commercial districts of the city. The expansion that followed was not dramatic in the way that revolutions are dramatic. It did not happen in a single season or announce itself with a visible event. It happened the way infrastructure always happens, incrementally, neighborhood by neighborhood, city by city, following the capital that paid for it and the demand that justified the capital, moving outward from the urban centers where the economics were most favorable toward the smaller towns and rural areas where they were least. In the cities, the process was visible in the changing character of the streets. The gas lamps that had lit urban streets since the early 19th century. Tall iron posts with glass globes enclosing an open flame, tended by lamplighters who moved through the streets each evening with long poles, were replaced gradually and then with increasing speed by electric street lamps that came on automatically at dusk and burned with a steadier, whiter light than any gas flame could produce. The change was noticed. People commented on it in letters and diaries and newspaper columns. The quality of the new light, its evenness, the way it made the night feel different from how it had always felt, more navigable, less bounded. The darkness that had defined the hours after sunset since the beginning of human history was retreating, neighborhood by neighborhood, from the centers of the cities outward, inside the buildings that the new grid was reaching in. The changes were quieter, but no less significant. The electric motor was, in the early years of the 20th century, doing to industrial production what the steam engine had done a century earlier, not replacing it exactly, but transforming the conditions under which it operated in ways that accumulated into something genuinely different. A factory powered by a single steam engine distributed its power through a system of leather belts and overhead shafts running the length of the building. each machine connected to the central power source by its own belt, running up to the rotating shaft above. The entire factory operated when the engine operated and stopped when it stopped. The layout of the machines was determined by their distance from the shaft rather than by the logic of the production process. Electric motors changed this entirely. Each machine could have its own motor, receiving power from the building's electrical supply, independently of every other machine. The factory floor could be arranged according to the sequence of production rather than the geometry of the belt system. Individual machines could be started and stopped without affecting the others. The productivity gains were significant, but the more lasting change was in the conditions of the work itself. Quieter without the clatter of the belt system, better lit without the gas flames that had previously served both for illumination and as an inadvertent source of heat and air pollution inside the building. The home was slower to change than the factory or the street, not because the technology was unavailable, but because the economics were different. Connecting a house to the electrical grid required the infrastructure to reach the street outside, and wiring to be installed within the walls, and devices to be purchased that could use the current once it arrived. Each of these steps required expenditure that not every household could justify or afford. The first electrical appliance to achieve wide domestic adoption was the electric iron, which arrived in American homes in the first decade of the 20th century and spread quickly because its benefit was immediate and its operation required no new skill. You plugged it in, it got hot, you ironed your clothes. The domestic electrical revolution, such as it was, proceeded from this kind of simplicity. Appliances whose function was immediately recognizable, whose benefit was concrete and daily, whose operation required no understanding of the underlying technology. The electric fan, the electric kettle, the electric toaster, which arrived in American kitchens around 1910 and produced the particular small domestic pleasure of bread becoming crisp and warm by a mechanism invisible within the metal walls of the device. Each appliance created a new expectation. Once a household had an electric iron, the absence of electricity, the return to a coal-heated iron, heavy and requiring constant management, became not simply an inconvenience, but a deprivation. The grid, once it reached a household, became rapidly indispensable, not because anyone had planned this outcome, because the things it made possible were easier than the things it replaced, and ease, once experienced, is very difficult to give back. In rural America, the grid was slower to arrive. The economics of extending transmission lines to farms and small towns spread across large areas with low population density were unfavorable by the standards of private electrical utilities, which built infrastructure where the returns justified the investment and declined to build it where they did not. By 1930, Nearly 90% of urban American homes had electricity. By the same year, fewer than 10% of rural farms did. The farmhouse, after dark in 1930, looked, in its essential character, much as it had in 1880 or 1850 or a century before that. Lit by oil lamps or kerosene, the kitchen stove burning wood or coal, the rhythms of the evening determined by the availability of light and the cost of fuel, rather than by any switch on any wall. The farmer's wife, who had read about electric refrigerators in a mail-order catalog, or who had visited a relative in the city and seen electric light in a kitchen for the first time, returned to her own kitchen with a precise and specific knowledge of what she did not have. The absence had been named, and a named absence is a different thing from a simply unknown one. The transmission lines moved outward from the cities slowly through the late 1920s. Following the roads in many places, their wooden poles set at intervals. Along the verges, the wires strung between them sagging slightly in their long, gentle curves. Where they reached, the change came quickly. The wiring of the farmhouse, the installation of the first bulb in the ceiling of the kitchen, the evening when the switch was thrown for the first time and the room filled with light of a quality and steadiness that no lamp had ever produced. People who experienced this moment for the first time described it in terms that suggested something more than mere convenience. A sense of the world becoming larger, or time becoming longer, or the night becoming less of an ending and more of a continuation of the day. The darkness outside the windows was the same darkness it had always been. But inside, the light burned on, steady and patient, and entirely indifferent to the hour. And the long, slow transformation of the world by electricity, begun in Gilbert's candlelit study, carried through Franklin's stormy field and Faraday's basement, and the turbine rooms of Niagara, continued its quiet work of becoming ordinary. The Rural Electrification Administration was established by executive order in May of 1935, during the deepest years of the American economic depression, and its mandate was straightforward in its statement and enormous in its ambition: bring electricity to the farms. Not as a commercial proposition, the private utilities had already demonstrated, through a decade of inaction, that the commercial proposition did not work at the densities and distances involved in rural America. As a public undertaking, the stock, a deliberate decision by the federal government that access to electrical power was not a luxury to be distributed by market forces, but a condition of modern life to which all citizens had a reasonable claim. The administrator appointed to run the program was a Texas lawyer named Morris Cook, and he approached the task with the methodical efficiency of someone who has been given a large problem and a limited budget, and has decided that the most useful response is to begin immediately and adjust as he goes. The Rural Electrification Administration did not build power stations. It lent money at low interest rates over long repayment periods, to rural electrical cooperatives that would build their own distribution lines and connect their own members to the existing grid. The cooperatives were formed by the farmers themselves. Neighbors gathering in schoolhouses and church halls in the evenings. By the light of the oil lamps they were trying to replace, to sign papers establishing the legal entity that would borrow the money and build the lines. And eventually, if everything went according to plan, bring electricity to every farm represented around the table. The line building that followed was physical work of considerable difficulty. The terrain of rural America did not arrange itself conveniently for the stringing of electrical lines. Hills, rivers, dense woodland, rocky ground that resisted the digging of post holes. All of these had to be negotiated, farm by farm, mile by mile, by crews of men, with hand tools and wooden poles and reels of wire loaded onto flatbed trucks that moved slowly along the dirt roads, connecting the properties to be served. A pole gang, the crew responsible for setting the wooden poles that would carry the wire, would work through a section of terrain in sequence, marking the pole positions, digging the holes by hand, or with a mechanical auger where the ground permitted, setting the poles, tamping the earth firm around each base, attaching the cross arms and the glass insulators that would hold the wire clear of the wood. Behind them came the wire crew, unspooling the copper conductor from heavy reels, pulling it taut between the insulators, connecting each section to the next with the particular splice that held under tension without adding resistance to the circuit. The work was slow. A good day might see a mile of line completed. A difficult day, rocky ground, a river crossing, a section of dense timber that had to be cleared before the poles could be set, might yield a quarter mile. But the lines moved forward day after day through the farms of the American South and Midwest and Great Plains, bringing the grid to places it had never reached. When the line reached a farm, the connection process followed a sequence that had become standardized through repetition. An electrician would wire the farmhouse, running cable through the walls, installing the ceramic fixtures that would hold the bulbs, fitting the switches by each door, and the outlets in the kitchen and the barn. The work took a day or two, depending on the size of the house and the number of rooms to be served. Then the line crew would connect the house to the distribution line outside, and the meter would be installed, and someone, usually a representative of the cooperative, sometimes the electrician himself, would find the main switch and turn it on. The accounts of this moment, recorded in letters and diaries, and the oral histories collected by researchers in the decades afterward, have a quality of unexpected emotion that the bare facts of the technology do not prepare you for. A farm woman in Arkansas, writing to her sister in 1939, described the evening the electricity came to their house. Her husband had been outside watching the linemen make the final connection. She had been in the kitchen, standing near the switch by the door. He came in. He nodded. She turned the switch, the bulb in the ceiling, a single bulb in a plain ceramic fixture, nothing elaborate, nothing different from 10 million other bulbs in 10 million other ceilings, came on. She wrote that she stood and looked at it for a long time without moving, not because it was beautiful, though it was in its way, but because it was steady. It did not flicker in a draft, or require trimming or fill the room with the faint smell of burning oil. It simply burned at a consistent brightness. For as long as the switch remained on, she had spent 30 years managing light that required constant attention. Here was light that required none. The appliances followed the electricity into the farmhouse, arriving in the sequence that economics and practicality dictated. The electric iron came first, almost universally, because it was inexpensive and its benefit was immediately clear. The labor of heating a cast iron on a wood stove, waiting for it to reach temperature, testing it against a damp cloth, working quickly before it cooled, returning it to the stove, and waiting again, was replaced by the thoughtful act of plugging in a device that maintained its temperature automatically and required no further attention. The electric pump came next for the farms that had wells. Before electricity, water was raised by hand pump or by a windmill whose operation was subject to the availability of wind. An electric pump delivered water at the turn of a tap at any hour, regardless of weather. The refrigerator arrived in rural homes through the late 1930s and the 1940s, replacing the icebox. A wooden cabinet insulated with sawdust or cork, kept cool by a block of ice delivered by the iceman, whose rounds through rural areas were a fixture of warm weather months. The icebox required planning. The ice had to be ordered, delivered, and managed, and the food inside arranged to account for the temperature gradient between the top of the cabinet, where the ice sat, and the bottom, where temperatures were higher. The electric refrigerator required nothing beyond being plugged in and set to the desired temperature. It maintained that temperature continuously, automatically, without any intervention from the household. The radio had arrived in American homes, both urban and rural, somewhat ahead of the full electrification of the countryside. Battery-powered sets had been available since the early 1920s, and the battery radio had become, in many rural households, the first piece of electrical technology they owned, the single concession to the modern world that the absence of grid power permitted. When the grid arrived and the electric radio replaced the battery set, the change was noticed primarily in the improved quality of reception and the elimination of the recurring cost and inconvenience of battery replacement. But the radio itself, the presence of voices from distant cities in the kitchen, of a farmhouse on a winter evening, had already done its work. It had changed the texture of rural isolation in ways that mattered before the grid arrived and continued to matter after it. A farmer in Iowa in 1932, listening to a battery radio in a kitchen lit by a kerosene lamp, could hear a baseball game being played in Chicago, or a political speech being delivered in Washington, or a concert performed in a New York studio. The distance between his kitchen and those events was the same distance it had always been, but the silence that had previously filled that distance, the silence that made distant events feel genuinely remote, genuinely other, genuinely unreachable, had been replaced by a voice speaking clearly from a box on the shelf. The world had gotten smaller, not physically, only acoustically, only in the particular way that information changes the experience of distance without changing the distance itself. By 1950, nearly 90% of American farms had electricity. The transformation that had taken urban areas 2 decades had been compressed in rural areas into 15 years of deliberate government-supported infrastructure, construction, the poles and the wire and the cooperatives, and the low-interest loans, all working together to cover ground that the market had declined to cover on its own. The farmhouses that had been lit by oil lamps in 1935 were lit by electric bulbs in 1950. The water that had been pumped by hand was pumped electrically. The food that had been kept in an icebox was kept in a refrigerator. The ironing that had required a cast iron implement heated on a wood stove was done with an electric iron that heated itself. None of these changes were dramatic, considered individually. Each one was simply an easier version of something that had been done before, accomplished by a different mechanism, but accumulated across an entire household, across an entire way of life. They amounted to something that the people who lived through them sometimes struggled to articulate. A sense of time having expanded, of the day having grown longer, of attention that had previously been consumed by the management of light and water, and heat being available for other things. The lamp that needed trimming every evening, the fire that needed tending through the night in winter, the ice that needed ordering and managing through the summer. These were not large things individually, but they were constant things. They required daily attention, daily labor, daily management. The quiet, continuous overhead of a life lived without electrical power. When electricity removed that overhead, the time it had consumed did not disappear. It became available. What people did with it, how they filled the hours that the technology had freed, was not determined by the technology itself. It was determined by everything else about who they were and what they wanted. The switch was on. The light was burning. The rest was up to them. By the middle of the 20th century, electricity had become ordinary, not unimportant, not taken for granted in the way that truly invisible things are taken for granted. The switch was still noticed when it was flicked the bulb still appreciated when it came on in a dark room, but ordinary in the sense that it had been integrated into the structure of daily life so completely that its absence, rather than its presence, was the thing that required explanation. The grid hummed inside the walls of homes and offices and factories across the developed world. The appliances drew their current and did their work. The lights burned through the evenings and the nights, pushing back the darkness that had defined human existence for 200,000 years, until the darkness had become something chosen rather than something endured. Rassi, electricity had transformed the physical conditions of daily life. It had made the home warmer and brighter and quieter and more productive. It had changed the factory and the farm and the street. What it had not yet done was think. That transformation, the one that would eventually dwarf everything that had come before it in its consequences for human life, was about to begin in a research laboratory in New Jersey in the winter of 1947, with a small assembly of germanium and gold foil and thin metal strips that sat in the palm of a hand and changed the world without making a sound. Bell Laboratories in Murray Hill, New Jersey was, in 1947, the most productive industrial research facility in the world. It was funded by the profits of AT&T, the American telephone monopoly, and its mandate was to conduct the basic scientific research that would keep AT&T at the forefront of communications technology. The arrangement was unusual, a private company funding pure scientific research without requiring any immediate commercial application. And it produced, over the decades of its peak operation, a body of work that included multiple Nobel Prize-winning discoveries and technologies that reshaped the modern world. The vacuum tube, by 1947, was the electronic device on which all of this rested. Computers used them. Amplifiers used them. Radio transmitters and receivers used them. The entire electronic infrastructure of the post-war world ran on glass envelopes containing heated filaments and metal plates, performing their functions reliably enough to be useful, but fragile enough to fail regularly, hot enough to require ventilation, large enough to make miniaturization effectively impossible. Bell Labs had decided, before the war, that the vacuum tube needed a replacement. Something solid, something that required no heated filament, something that could amplify an electrical signal without the mechanical fragility and the heat and the size of the tube. The research program they established to find this replacement was led by a physicist named William Shockley, and it proceeded through the war, years in parallel with the military research that occupied most of the laboratory's attention, slow and intermittent, waiting for the peacetime conditions that would allow it to accelerate. The two men who made the critical breakthrough were not Shockley. John Bardeen was a theoretical physicist of extraordinary mathematical ability, quiet in manner, precise in thought. the kind of mind that could hold enormous complexity in working memory and move through it methodically. Without losing the thread, Walter Brattain was an experimental physicist, a builder, a hands-on craftsman of scientific apparatus, Pilatus, whose intuition for the behavior of physical systems was expressed through the things he made rather than the equations he wrote. Together, in December of 1947, they constructed a device from a small piece of germanium, a semiconductor material whose electrical properties could be controlled by the addition of trace impurities. With two gold contacts pressed against its surface by thin strips of metal foil. When a small electrical signal was applied to one contact, it controlled a much larger electrical current flowing between the other contact and a base connection at the bottom of the germanium chip, a small input controlling a large output, amplification, without a heated filament, without a glass envelope, without the fragility and the heat and the size of the vacuum tube. The transistor, the device they demonstrated to their colleagues on December 23, 1947, was crude by any subsequent standard. It was assembled by hand, its components held in place by careful physical arrangement rather than any permanent bonding, its performance inconsistent between one test and the next. It worked, but barely, and only under conditions controlled enough to eliminate the variables that would make it fail. But it worked. Brattain's laboratory notebook entry for December 23, 1947 describes the demonstration with the characteristic understatement of an experimental physicist recording a result. This circuit was actually spoken over, and by switching the device in and out, a distinct gain in speech level could be heard and seen on the scope presentation, with no noticeable change in quality, a distinct gain in speech level. Heard and seen, the age of solid-state electronics had begun. Recorded in a laboratory notebook in handwriting that gave no indication of the weight of what was being documented. The transistor was announced publicly by Bell Labs in June of 1948 at a press conference that attracted modest coverage in the science sections of American newspapers. The New York Times mentioned it in a column on Radio News, noting that Bell Telephone Laboratories had invented a device called a transistor that might have applications in radio technology. The coverage was accurate and entirely insufficient. The transistor would not simply have applications in radio technology. It would make possible every digital device that has existed since. Every computer, every mobile phone, every server, every piece of electronic equipment of any kind that has been built in the 75 years following that quiet press conference. But these consequences were not visible in 1948. Only the device was visible, and the device was small and difficult to manufacture consistently, and not yet ready for the commercial applications that would eventually justify the investment in making it better. The making it better took the rest of the decade, and the next decade, and the decade after that. In 1958, an engineer named Jack Kilby at Texas Instruments solved a problem that had been limiting the development of transistor-based electronics since the device's invention. The problem was connection. A transistor could amplify a signal, but useful electronic circuits required not just amplification, but the combination of many transistors with other components, resistors, capacitors, the elements that together performed the logical and mathematical operations that electronic devices were being asked to perform. Each component had to be manufactured separately, then connected to the others by hand. Tiny wires soldered between tiny terminals by skilled workers under magnification, a process that was slow, expensive, and subject to the accumulated unreliability of many individual connections, each of which might fail. Kilby's insight was that all of these components could be made from the same piece of semiconductor material, their connections formed as part of the manufacturing process rather than assembled afterward. He built the first integrated circuit, a small chip of germanium on which a transistor and several other components had been formed simultaneously, connected by conducting paths deposited on the surface of the chip during manufacture. It was small, it was crude, it worked. Robert Noyce at Fairchild Semiconductor developed a similar device independently, using silicon rather than germanium, and a manufacturing process better suited to commercial production. The integrated circuit, the chip, was born simultaneously in 2 laboratories by 2 men working independently, as fundamental advances in technology occasionally are when the underlying conditions have matured to the point where the breakthrough is waiting for whoever arrives at the right question first. The chips grew more complex with each year, not slowly, at a rate that an Intel engineer named Gordon Moore described in 1965. After examining the trend in the number of components that could be placed on a single chip, the number was doubling approximately every 2 years as manufacturing processes became more precise and the features etched onto the silicon surface became smaller. Moore's observation became Moore's law, and Moore's law held with remarkable consistency for the following 5 decades. Every 2 years, roughly twice as many transistors on a chip of the same size. Every 2 years, electronic devices capable of performing roughly twice as many operations per second, or capable of performing the same operations in half the space, at half the cost, consuming half the power. The compounding of this doubling, sustained over 50 years, produced results that defy intuitive comprehension. A chip manufactured in 1980 might contain tens of thousands of transistors. A chip manufactured in 2020 contained tens of billions. The same fundamental device. The transistor, the solid-state amplifier that Bardeen and Brattain had assembled from germanium and gold foil in a New Jersey laboratory. In December of 1947, reproduced at a scale and a density that the men who invented it could not have imagined, performing operations at a speed that no human mind can directly perceive in a space smaller than a grain of sand. The computers that emerged from this process of continuous miniaturization moved over the decades between 1950 and 1980 from the room-filling machines of the ENIAC era to devices that fit in a single cabinet, then on a single desktop, then eventually in a single chip, smaller than a fingernail. The electricity that powered them followed, not the high-voltage current of the grid, transformed down through substations and distribution lines to reach the wall socket. The delicate, low-voltage, precisely controlled current that flowed through conducting paths on a silicon surface, switching on and off billions of times per second, representing ones and zeros in patterns that could encode any information that human beings had yet thought to encode. The bulb at ceiling of the farmhouse and the transistor on the chip were both electrical. Both depended on the same fundamental force that Gilbert had named and Franklin had pulled from a storm cloud and Faraday had coaxed from a coil of wire in a basement. But the distance between them, in scale, in precision, in the nature of what the electricity was being asked to do, was the distance between a hammer and a scalpel. Both were tools, but they were tools for entirely different kinds of work. The hammer had built the physical world. The scalpel was about to build something else, something that had no weight and no location and no physical presence of any kind, something made entirely of ones and zeros, running on electricity so small and so fast that it existed, for practical purposes, in a different dimension from the current that lit the room in which the computer sat. The transistor had made this possible, and the transistor was made of the same force that had twitched a dead frog's legs in a laboratory in Bologna in 1780, while a physician named Galvani watched and wrote careful notes in the margins of his understanding. The electron had gone smaller, and in going smaller, it had become everything. There is a moment in the life of every technology when it disappears, not when it becomes obsolete or is replaced by something newer or fades from use, but when it becomes so thoroughly embedded in the structure of daily life that it ceases to be perceived as technology at all, when it becomes simply a condition of existence, as unremarkable and as essential as the air in a room. Electricity reached this moment somewhere in the last decades of the 20th century in the developed world and has been reaching it in the rest of the world ever since, arriving in villages and towns and rural districts that had existed without it for centuries, and becoming, within a generation of its arrival, something that the people who grew up with it cannot imagine having lived without. The grid that Edison began in Lower Manhattan in 1882 with 59 customers now spans continents. It runs through undersea cables, crossing ocean floors at depths where no light reaches. It climbs mountain ranges on steel transmission towers whose footings are set in rock at altitudes where the air is thin and the weather is violent. And the work of installation was done by people whose names appear in no history. It crosses deserts and tundra and the vast agricultural plains of 3 continents, carrying current from the places where it is generated to the places where it is needed, following demand through a network so large and so interconnected that its total behavior at any given moment is beyond the ability of any individual or any computer system to fully model. The sources from which this current is generated have changed and are changing still. For most of the 20th century, the majority of the world's electrical power came from burning things, coal primarily, the same material that had heated the homes of the industrial era and powered the steam engines that drove its factories, now burned in power station furnaces to produce steam that turned turbines that drove generators, the same electromagnetic principle that Faraday had demonstrated in his basement, scaled up to produce current for millions of customers simultaneously. Natural gas followed, and oil and nuclear fission. Uranium atoms split in controlled reactions, their heat used to make the steam that turned the turbines, that drove the generators. Different fuel, but the same fundamental conversion of heat into motion, into electricity. The environmental consequences of burning fossil fuels at the scale required to power the modern world became, in the final decades of the 20th century, a problem that could no longer be deferred. The responses that emerged were not new in principle. Wind had been used to do mechanical work for centuries. Solar energy had powered the Earth's biological systems since before life existed. What was new was the technology for converting these sources into electrical current at efficiencies and costs that made them competitive with the burning of coal and gas. Solar panels, devices that convert sunlight directly into electrical current through the photovoltaic effect, a phenomenon first observed in 1839 by a French physicist named Edmond Becquerel, had existed since the 1950s. They had powered satellites and remote equipment where no grid existed, and no other power source was practical. But for decades, they were too expensive to compete. With fossil fuels for large-scale generation, the cost fell. Year after year, through the 1990s and 2000s and 2010s, driven by the same compounding improvements in manufacturing that had made transistors cheaper. The cost of a solar panel fell until, in the 2020s, it was cheaper to generate electricity from sunlight in most parts of the world than to burn coal to produce the same amount. Wind turbines followed a similar trajectory, their blades growing longer and their generators more efficient, their installations moving offshore where the wind was stronger and more consistent, and the visual impact on inhabited land was reduced. The grid was changing its sources without changing its essential nature. Still, a vast network of transmission lines and substations and distribution cables, still delivering alternating current at the frequencies and voltages that Tesla and Westinghouse had established in the 1890s, still carrying the electricity from wherever it was generated to wherever it was needed. The electricity that arrived at the wall socket in a modern home was doing things that no one in any previous century could have described, because the things it was powering did not exist in any previous century. The server farms that held the data of the internet, vast warehouses filled with racks of computers running continuously, their processors performing billions of operations per second, their cooling systems consuming nearly as much electricity as the servers themselves, drew current from the grid in quantities that made them among the largest electrical consumers in the regions where they were located. A single large data center might consume as much electricity as a small city, and the world, by the 2020s, contained thousands of them, located in the cold northern regions where the outside air could be used for cooling, or near rivers whose water could perform the same function, or in places where the electricity was cheap enough that the cost of running the servers was manageable. All of this, every photograph uploaded, every message sent, every video streamed, every search query answered, required electricity, not in the quantities that a household appliance required, but accumulated across billions of users performing billions of actions every day. The total was enormous and growing. The internet, for all its apparent immateriality, its invisibility, its weightlessness, its existence as pure informations, flowing through fiber and radio, was a physical infrastructure that ran on electricity and required electricity to exist. The cloud had a weight. It just happened to be distributed across enough locations that no single place felt it. In a village in rural Kenya, a woman charges her mobile phone from a small solar panel mounted on the roof of her house. The panel was installed 2 years ago through a program that provides solar home systems to households without grid access. The battery it charges during the day powers the phone and 2 LED lights and occasionally a small radio. Through the evening and the night, she did not have electricity before. She had kerosene lamps, which she managed with the careful economy of someone for whom fuel costs money, and money is not abundant. The lamps produced light sufficient for basic tasks, cooking, moving through the house after dark, but not for reading, or for the children to do homework by, or for any of the things that adequate light makes possible and inadequate light does not. Now she has light that costs nothing to operate once the panel is paid for. And she has a charged phone, a connection to the mobile network, to mobile money, to the agricultural price information services that tell her what her crop is worth in the nearest market before she decides whether to sell it today or wait. The electricity reaching her home traveled no transmission line. It came from the sun. 8 minutes after leaving its surface, converted by silicon cells into current that charged a battery that powered her life. Faraday would have recognized the principle. The scale would have astonished him. Tonight, in homes across the world, the electricity is doing what it does every night. It is keeping the refrigerators cold and the routers blinking, and the charging cables pulsing their small, steady currents into the batteries of the phones resting on bedside tables. It is running the servers that hold the data of the lives people have built online, the photographs and the messages, and the records of 10,000 ordinary days stored in buildings most people will never see, in places most people could not name. It is moving through the walls of the room where you are lying, through wires run between the studs, through the breaker panel in the hallway, back through the meter on the outside wall, into the distribution line on the street, back through the substation at the edge of the neighborhood, into the transmission line that runs to the power station 30 miles away, where a turbine is turning in the dark. The turbine turns because something is pushing it, water or steam or wind, or the slow accumulation of photons that arrived from the sun during the day and were stored in a battery until they were needed, and the electricity flows because Michael Faraday spent 20 years in a basement winding coils of wire around iron cores, and because Alessandro Volta stacked discs of zinc and copper in a column in a cold room in Pavia, and because Benjamin Franklin stood in a field in Philadelphia with a kite and a key and a question that had been waiting 2,000 years for someone patient enough to answer it. The switch on the wall is the end of a very long story, and tonight it is on. The room is lit. The world is running. And somewhere in the walls, the invisible force that changed everything moves on in its patient, endless, ordinary way. Seep meek well. The series is complete. If this quiet journey through the history of electricity helped you rest tonight, a like or subscribe means the world. Sleep well.